So let me continue from yesterday's talk. So I will discuss the parabolic GUI method. So yesterday I discussed the L2 case, the inner outer GUI for the energy critical, and we consider the dimension 5, and we want to construct a blowup solution with this blowup rate. And so the whole idea is to write the solution in this form. So this is the leading order, and this is the noise term, and then the inner part and the outer part. So the inner problem is a linearized parabolic problem, and the outer problem is just a parabolic. Okay, and so the outer to inner is do this term, and the inner to outer to the cutoff function. And so we have this this problem. It's decoupled. So we only need to estimate these two terms, and this outer to inner, and the inner to outer. Okay, this is the cutoff function. So yesterday, we construct a solution which decays everywhere. But in practice, all we need is a solution that decays near the boundary. So what we did yesterday is the L2 case, and we solve for this linear problem, and we assume we have fast space decay and time decay. Then we have a same solution. We have a solution with the same time decay and a little bit of space decay. So this is almost like the elliptic case. Okay, almost like an elliptic case. So so this is the L2 case, because this is the case when n greater than 5, and we can take a limit. Now, when n equals 3 and 4, this L2 does not make sense anymore. So you cannot take this limit, okay? And in that case, you cannot do uphill estimates, because you just simply, you cannot use orthogonality condition. And so this is the case in dimension 3 and 4, and then later I will talk about the dimension 2. Okay? So in these dimensions, you see the major difficulty, which is non-L2, which is the kernel is not in L2, and this is what I'm going to discuss today. Okay, so the main result I will discuss today is dimension 4, and the p equals 3. So there's a critical exponent m plus 2 over m 3. And for t sufficient small, and we want to construct an initial condition so that the blob happens exactly at some place q. And the blob in the leading order looks like the Waban-Atlantic bubble, but the blob rate is log square over t minus t. So in the first theorem, in the dimension 5, the blob rate is t minus t square, cube, sorry, is algebraic. But here the blob rate is quite a strange blob rate, and later we're going to see how this blob rate was derived, was derived. Again, the blob is called dimension 1 unstable. Okay, so we just do the regional symmetry case. I want to catch the main idea, okay, in the regional symmetry case. Okay, so we go back to the formal computation, and we start with the ansatz, and this is our ansatz. Now dimension is 4, so this is 1, okay? And so we have this one plus percent 0. So plug into, and the percent 0 satisfies the linear heat equation. Okay, and we plug in, we compute the error. It's the same as in dimension 5. This is a formal computation, and we get two terms. The first term is the error from the outer problem, and the second term is the scaling. Okay, so the scaling is, I call it Zn plus 1. Okay, so this is the same as dimension 5. This is the same dimension 5. Now, what is the main difficulty in dimension 4? So in dimension 4, if p equals 3, the profile decays like 1 over y square, and the kernel also decays like 1 over y square. So the error here is not even L2. Okay, so this one is L2. This one decay fast, but this one is not in L2. So if it's not in L2, then you can destroy any solvability theory in parabolic setting because this is not L2. So we need to take care of this time because it's not L2. Okay, but the major problem, another more difficult problem is the slow decaying kernel. So the kernel here, we have 4 translation kernel, and we have 1 scaling kernel. But this scaling kernel, this Z5, decays like 1 over y square. It's like U. And this is barely L2 because you lose L2 by a log. Okay. So this function is not L2, and the error is not L2. We have these 2 main difficulties, and we have to deal with it. And we do this one first. Okay, this is relatively easy to deal with, but this is the major difficulty because here I cannot do any blowup. Okay, any blowup I don't know how to, because any blowup I cannot take a limit. Okay, so let me first deal with the first difficulty. How to deal with the slow decay. Okay, this one has a slow decay. Okay, so this part has a slow decay, and this, if we write in this form, you see that this is like 1 over y square is not L2. And so if we go back to the original x, this term is like natural prime over 1 over x squared. It has identical singularity at 0, but it's not L2, okay, in the global sense. So what we do, we correct this term with a global term. So what do we do? We solve. This is our error, which has a slow decay. We solve this problem with the Duhamel formula. Okay, we solve this heat equation with this slow decay error, and we compute. There's a formula for this, and this formula is given by the Duhamel formula. But we're going to take a special form of the solution in the self-similar form. And in the self-similar form, this problem can be solved, okay? And so we're going to include this as our new, add this to the answers, because this will kill this slow decay term, okay? So we're going to add this this term. This term is a global term, and this term is very important. As I told before, we have a very strange block rate. Okay, it's t minus t over log square, and this strange block rate precisely come from this term. Okay, come from this global term, okay? And as we're going to say later. Okay, so now we solve this problem. So with the introduction of this global term, our new error will have faster decay. Okay, this will be good. Our new error will be like u square, and the u is like 1 over y square. U square will be 1 over y to the 4, and so we have faster decay. Okay, so now just a remark that this, if you add the global term, this global term is nothing but you are losing like the projection of the bubble and to the parabolic problem. Okay, so we go to the inner problem, and we go to inner. So we do the inner variable, inner variables y and tau, just the same as in the dimension 5 case. And so in the inner variable, the approximate solution is like 1 over 1 plus y squared. There's some constant here. Okay? All right. So the inner solution, inner equation is phi tau equals Laplace phi plus 3u square phi plus some error terms plus some terms come from the global correction, and there's also an outer problem comes from the outer problem, and then there's nonlinear terms and so on. Okay, I call all this as H. Okay, this part I call the error as H. Okay, and the outer problem is the same as before. So the outer problem we get the cutoff function. Okay, so 2 times gradient eta gradient phi plus 5 times the Laplace eta r. Okay, so the coupling from inner to outer to inner is through this term 3u squared per psi, and the outer to inner is through this cutoff function. Okay, through this cutoff function. Okay, so the key observation, as I said last time, is that in order that the inner and outer problem are decoupled, we only need to estimate the outer to inner, which is 3u squared per psi, inner to outer, which is the cutoff function. Now, we don't care what happens for the inner problem inside the domain. Okay, because of the cutoff you only need the behavior of phi near the boundary. Okay, this should be eta r. Okay, so this is the key element in the non-L2 case, because in the non-L case, the solution we get will be very bright inside. However, the solution has little bit of decay near the boundary. So this is the main takeaway from this non-L2 green is that the inner solution you obtain because you cannot do bluff argument, so you're going to lose a lot of will be very big, okay, inside. But fortunately, the inner solution decay I have little bit decay near the boundary, so we need to construct such kind of solutions. Okay, so let's do the most difficult case, which is the reduced symmetric case. So we phi is phi 0 r, and we have this linear operator, okay, and plus h, and we assume everything reduced symmetric, and we also assume the solution is orthogonal. The h is orthogonal to Z5. Okay, and we choose some special direction because we need to get rid of the unstable direction. Okay, so this is the problem. Okay, so you see that in this problem here, I only ask h to be orthogonal to Z5, and I don't ask phi to be orthogonal to Z5. Why? Because Z5 is not L2. My H, I can have a faster decay. Okay, the H can have faster decay, but my solution, I know that it does not have fast decay. So integral phi times Z5 equals 0 does not make sense. Okay, so I can only I can only impose the condition on H, but I cannot impose the condition on phi, and we need to find a phi, okay, for this problem. There may be many solutions to this problem, but we need to find a good solution. Okay, so the main result is the following. Suppose we have a decay in time and decay in space, and then for sufficient large R, we can find a solution phi and C0, so the initial condition, such that phi decays the same as time decay, tau to the minus mu, and r to the 4 minus sigma log r over 1 plus y to the 4. So let's look at this term. If y is order 1, this is extremely bad because you lose r to the 4. basically you lose R to the 4 times log R. Okay. However, if you are near the boundary, near y equals R, then this one decays. This one is like 1 over R to the minus sigma, because when y equals R, this is R to the minus sigma. Okay, so this is the solution we construct. In the inner part, it is really big. Okay, it's like R to the 4 log R is. And remember, in many of the problems, our R is basically is like tau. Okay, tau. So so you lost a lot of time decay inside. Okay. However, near the boundary when y equals R, and this term is R to the minus sigma. So you gain some decay. And the decay, this is good. You gain some decay, so the outer green can work. Okay. However, the first part, the R is really big. This creates a huge problem for nonlinear terms later, since we have to take a cutoff far away to gain regularity. And the cutoff we're going to get is tau to the 1/3. Okay, remember, square root tau is the self-stable regime. So it's very close to square root tau, which is then you lose a lot of tau inside. And then you will take a nonlinear term, you lose more tau, because nonlinear term is like a 5 square. So there's a trade-off, okay? There's a trade-off to do. Okay, so let me now show you how we prove this result. Okay, prove this result, and we do this. Okay, we don't impose any condition on phi. Okay, we don't assume phi is orthogonal to Z5 because this does not make sense because it's not L2. But we do assume that the right-hand side is orthogonal to Z5. Okay. So first, by elliptic theory, you can use you can use a Friedholm, and if fixed H, okay, and remember H depends on Y and the tau. So fixed H is orthogonal to Z5. You can find a solution H, and this H will have the same decay like H, you lose 2 power. Right? This is Y to the 2 per sigma, this is Y to sigma. Okay. So first we use the elliptic problem, we use the elliptic to solve H. Okay. And this is okay. We have Friedholm theory. So as long as our solution is H is orthogonal to Z5, we have a solution. We have a decay solution. So this part we use the elliptic theory. Okay. So, and in the second step, we solve the problem, the linear problem with the H, with the big H. So this big H is the elliptic problem. So I just drop the T, the tau, and we solve the elliptic problem. I get a solution. Okay. And then what I do is I solve the parabolic problem with this elliptic solution to the elliptic problem. Now, for this problem here, I cannot impose any condition for H because I don't know, right? H only decay a little bit, okay? And now, how do we find a solution? There are many ways to find a solution for this problem. So we found a solution with the diffusion boundary condition. Okay. And we need to get rid of the unstable mode. So Z0 is exponential decay, is an unstable mode. So this is okay. I can impose this condition. And I also just put zero initial condition. Okay. So my claim is for this problem, I can find a solution. Okay, and this problem and the solution satisfies R to the 4 minus sigma log R divided by 1 plus y squared. Okay, so my y has just a little bit of decay. Okay, now I have a solution which loses a lot of R, so it's big. Okay, so think about h equal 1, just h equal 1. Think about it is Laplace. So my solution is almost like a constant. Inside is like R squared, and then on the boundary equals 0. Right? This is the kind of solution we have. Okay, so this is so this solution when y equals R is like R to R squared, and so you lose lot of R's. Okay, lot of R's. Okay, so this is the key step. If we can solve this step, so let me just recall in the step 1. So the equation, this is the equation I need to solve. Okay, with h. So in the first step, I just dropped this equals 0. I found a big h. Okay, this is my first step. Now in the second step, I use this big h as my source. I solve the parabolic problem. Okay. So, and I get a solution with a lot of growth in R. Okay. Now what I do is from this solution here, I take L0 of this solution. I take second order derivative of this solution. Okay. Now remember, this big phi solves phi tau equals L0 phi plus h minus c times z0. So if I put L0, I get x0 on both sides. So I can take out L0, L0 phi tau. I can take out tau here, and L at 0 times L0 phi, which is little phi. But L0 h is the infinite problem I already solved. And this one, L0 z0 is just lambda z0. Okay, so the phi solves this problem. Okay, and this is exactly what I want. Okay, this is exactly the solution I claim for the mode 0. Okay, so let me just repeat. First, I solve the elliptic problem. Okay, I get a big h. Then I use this big h as a source. I solve the parabolic problem without putting any any condition. Okay, and then I take L0 times big phi, and this will be the solution I want. Okay, exactly the solution I want. Okay, and this solution is like R to the 4 minus sigma log R and 1 plus y to the 4. Okay, so these are the 3 steps. So the major step is this one. Is the one with some source and the low orthogonality condition on Z5, and we need to find a solution, find the estimate for this problem. This problem, you also have a solution. You just need to estimate what is the behavior of the solution. Okay. So the main problem is to prove step 2 is the linear theory without orthogonality condition. And the estimates are very bad, and whereas we expected. So the equation is the linear versus parabolic equation, and we have this decay here, little bit of decay here, and we want to find a solution that loses a lot of R, but we have little bit decay in Y. So first, we concentrate the error because we don't like this decay too small. Okay, so what we do is we use a cutoff function and we solve the problem outside a bigger ball. And this and this problem has a unique solution. And the reason is this operator, okay? This operator does not satisfy maximum principle, okay? And there's a kernel which is Z5, right? And it changes sign. But however, you only change the sign for y less than 1. One on y greater than 1, this function, the kernel here is strictly positive. So I just cut the part where Z5 is negative, and I solve this problem. Well, this problem you can solve by maximum principle because it satisfies the maximum principle. And so by barrier, and you found a solution. Okay, this is found a solution with a good decay. And then the remaining part will be concentrated. Okay, will be concentrated. So now this one has a faster decay now. Okay, so for this faster decay, I can just say so that this equals 0. Okay, is orthogonal to Z0. All right. Okay. So for the problem with fast decay, there is with diffusion boundary condition, and you can there's always a solution, and the problem is what is the a priori estimate for the solution. Okay, so if we do the energy method, but in the parabolic case, we multiply both sides by 5, and we get this and this and this. Now, the problem is this conjecture form here. Okay, we don't whether or not it's positive, we don't know, and how positive it is. And since the dimension is 5 and phi 2 equals 0 on the boundary, then you can show that this conjecture form is coercive. Okay. However, the constant is very small. The constant is like C over R squared log R. It's very small, but it's coercive. So with the constant, with the R squared log R, and using the ground hole inequality, and you get the L2 estimate, and with the L2 estimate, by standard parabolic estimate, then we get L infinity estimate. Then once you have L infinity estimate in finite region, then you use the maximum principle far away. You can use maximum principle far away, and so that's why you get this kind of decay because the decay for the kernel is 1 over y squared. So that's how you get this 1 plus y squared. Okay, so the main problem for this problem is the estimate inside in the region where y say less than 1, less equal to 2, because for y greater than 2 you have maximum principle, and so but inside the region where y less equal to 2, you lose a lot of r's. Okay, and so you have this estimate, and this is the main theory for the non-orthogonal case. Okay, so this is the linear theory in the case when you don't have L2. So you see in this theory here, we don't use blowup. Okay, because you cannot do RPA estimates, you cannot do blowup, and the only thing we have is energy. But even with the energy, you lose a lot of R's. Okay, there's a lot of R. So this is the main result. The linear theory for the dimension 4 case. As I said, this linear theory is not good because you lose a lot of R's. You have some decay, okay, for y equal R, but you lose a lot of R's inside. And but you can use the same idea and do a secondary, okay, the secondary, in the outer green, you can cut a little bit inside more and do the same kind of inner outer green. And now with the expense that now you don't know what is the constant C, okay? You don't have what is the Lagrange multiplier, but you can do this kind of secondary in the outer green, and then you can lose just a little bit R inside. Okay, so we have the same inner and outer. Okay, inner and outer. We have the inner problem and the outer problem, and the same as before. And you do the inner and the outer growing, and in the end you need to solve the reducer problem. So the reducer problem approximately reduced to integral of HZ5 equals 0. And this gives you the OD, the equation for lambda. So let's try to understand this OD, okay, this equation, balance condition. So what is our H? Which have computed our H is basically is like a U square times, remember this is a global term, and this is a precise term. So, and the integral this one was equal to Z5, and do a lot of computation, and what you get is a non-local OD. It's a very strange OD, which is integral from minus t to t minus lambda squared t, and lambda dot and over t minus s ds. And this is basically your freeze the coefficient. Okay. So now the problem is to solve this problem. Okay. So this is a non-local OD. How to solve this non-local OD? Well, you know you want a lambda at t equals 0. Okay, so you cut a little bit before, okay, t minus t, and then you subtract lambda dot s and add lambda dot t, and so you get this this type of non-local ODE, and this type of non-local ODE is almost an ODE, and it's a second order derivative of this, and so from this you get a lambda is like a c over log square, and so you get lambda is log. Now this proof is really is a formal argument, and the reason is that I cannot differentiate. I can only differentiate lambda dot exists, but I don't know the second order derivative, because this is a regularity theory. You cannot use the second order derivative, you know, because this problem you don't know what if you only give you the first order derivative. It does not know the second order derivative. So but the idea, but this idea works. Okay, I mean this. What you need to do, you need to do a lot of approximations, and you solve this. Do a lot of approximations, and in the end you solve the non-local ODE as a local ODE, and you found this this number. And what you can show actually, the generic mode, you get a number data is 1 over log square, but you can also have non-degenerate blobs, like 1 over log cube, 1 over log 4, but the generic for most of the initial condition, you get a t minus t log t. And in fact, the blob, this is a stable blob. Okay, this is a stable blob. Okay, of course, we have this holder term. We have this one. We have to use the holder continuity, and so this means you have to take your cutoff very close to the self-similar part and to gain regularity. And so there's a lot of computation inside here, and but this is the basic idea. Okay? This is the basic idea. And so in dimension 3, you can do almost do the same, and you can get arbitrary. You can get a block rate of any t minus t to the power, and so for the inner part, you do the same with some global correction term, And for the outer part, you use the self-similar solution for the heat equation. So for the outer solution in the dimension 3 is no longer just the heat equation. You have to use self-similar blob for the heat equation, and you match the self-similar blob for the heat equation with the inner solution, and you get the blob rate. So the outer problem for the heat equation, self-similar for the heat equation, which is related to the Hamid polynomials, and that's why you get all this quantized rate. And for the linear theory, you lose a lot of you lose r to the 4 minus sigma. And the reduced problem is again is non-local, and what you can for this kind of problem you can use Laplace transform to solve. So I will not discuss this now. Okay, so what I have give you a tour of the Green method for dimension 5 and dimension 4, and now for dimension 3. And for dimension 5, and you just use the Gator Spark type, blob argument, okay, and you get RPL estimate. For dimension 4 and 3, and you have to use the construction to construct a solution, okay. And finally, another case is dimension 2, okay. Dimension 2 is where dimension gets lower, you get more difficult. So we have discussed the parabolic in the outgoing for dimension 5, okay, which is L2 case, and dimension 3 and 4, which is non-L2 case. What about dimension 2? So in dimension 2, the right problem is the new wheel. Is ut equals Laplace plus e to the u, okay, in R2. And the solution for the new wheel, the blowup profile is, you can all write down the blowup profile, and you get e to the u 8 over 1 plus y square and the square. So for this kind of problem, again, the kernel here is not even decay, right? The radial kernel just bounded, okay? So you have no decay at all. So for this type of problem, mainly is more difficult than dimension 3 and 4, right? In dimension 4, you have 1 over y square. Dimension 3 is like 1 over y, but in dimension 2, it's just purely just bounded. Your kernel is only bounded. Okay, so how do we deal with this case? So the main problem is to have a linear theory for the linearized new wheel. Okay, so the linear theory is the theory in R2. So it's phi tau equals Laplace phi plus e to the u phi plus h, and you want to get a linear theory for this equation, for this problem. Okay. Okay, so you have this kernel here. You have translation ones, okay, and you have this scaling one, which is just order 1. Okay, so we need a linear theory, need a solution with both fast space and time decay. Okay, so for these problems, all the modes are not L2. Okay, so even translation mode is just 1 over 1, which is not L2. And for the scaling mode, is not just L2, it's just bounded. At infinity is constant. Okay, because the operator far away is 2D Laplace, and we don't expect any special decay for 2D Laplace, and we expect to lose some logs. Okay, so how to get a good linear theory? Okay, for the new wheel, and for new wheel, instead we use a new method. This is a new method of finding good solutions. We don't have L2 kernel. And we use the so-called distorted Fourier transform. Okay, DFT. So let me just introduce now what is a distorted Fourier transform. So if we just consider the parabolic equation, the heat equation, ut equals Laplace u plus h, how do we get the fundamental solution? We get the fundamental solution by taking the Fourier transform on both sides. And so the Fourier transform will get this minus Cosine square. And then our solution is the inverse Fourier transform. Okay, and then you have this Duhamel formula. Okay, now our problem is ut equals Laplace u plus some potential times u plus h. Okay, so what we need is a Fourier transform which corresponds to this operator. Now, we want a Fourier transform so that this same property works. Okay, so that we take the transform. This gives a minus Cosine square times u height, and this is the so-called distorted Fourier transform. So the classical Fourier transform is a Fourier transform corresponding to Laplace operator, and distorted Fourier transform is a Fourier transform correspond to Laplace plus the Schrödinger potential. Okay, Laplace plus the potential. And so this kind of distorted Fourier transform has been developed by a lot of people, and in particular in this for the people in dispersive wave equation, the wave map, and there are also application of distorted Fourier transform. So let me just give you an idea of what is distorted Fourier transform. So you take a Schrödinger operator like this. So the original Fourier transform is like u second order derivative, correspond to u second order derivative. So with the Schrödinger operator, and for each psi, you found the two fundamental solutions, and then you can use these two fundamental solutions. You can define the so-called spectrum measure. Okay, and the spectrum measure is given by this Wronskian, which is the Weyl Tinchmark function. And with this spectrum measure, you can define a distorted Fourier transform, which almost like the same Fourier transform. So you can recover. This is the distorted Fourier transform using the spectrum measure. And with this, you can also recover your f by this. Okay, and this distorted Fourier transform agrees with the classical Fourier transform. Now, if V is 0, this is just a Fourier transform. If V is the Hardy term, C over rho square, distorted Fourier transform is just the so-called Hankel transform. But our problem is not Hardy. Hardy 1 over C over rho square is some function. Okay, this function comes from the new Weyl. Okay, come from the new Weyl potential, and so we need to develop the distorted Fourier transform with respect to this Schrödinger potential. And for this Schrödinger potential, you have these two kernels, and so they are changeable. So this becomes second order derivative, and the plus. You see, this is the Hardy potential. Okay, is V over R square. But then you have some extra terms here. Now, if you don't have this extra term here, this is just Hankel transform. This is a Hankel transform. But with this term, then the problem becomes more complicated. Okay, and so we can now define under the spectrum measure. So we have the unstable modes. Okay. And so what we need is to find the fundamental solution for NEC. You found a fundamental solution with this Röntgen, okay, and then you can compute the so-called this spectrum measure. Okay. Anyway, there's a lot of computation and lot of local expansions, and so for this spectrum measure, you have the density estimate. But once you have the discrete Fourier transform, you can now perform the same kind of operation like the Laplace operator. You take the discrete Fourier transform on both sides, okay, and then you get a cassette square outside, and then you get your fundamental solution, and then from the fundamental solution you can get the so-called the Duhamel formula, okay, and so you have this is the Duhamel formula for this operate for this problem with a Schrödinger potential. Okay, so fix each Schrödinger potential, you can define a Fourier transform, and with this Fourier transform, you can define a Duhamel formula. Okay, we can define the now with this Duhamel formula, and we can have compute. We can have a linear theory without orthogonality condition. In this case, you lose log as we expected. And with orthogonality condition, actually you don't lose log. You get a better estimate. So this is the another method in dealing with the slow decay of the kernel in dimension 2. Right? So all this with this answer you get exactly what you expect. You only lose a log without orthogonality condition, and you can use the dissolvation to deal with mode 1, but the discrete Fourier transform actually get loss a lot more R's than the theory we defined in dimension 3 and 4. Okay, finally, in 5 minutes, I will discuss some applications of this inner-outer growing method in singularities of geometric and physical flows. And I will give you an overview of the inner-outer growing for dimension 5, dimension 3 and 4, and the dimension 2. And so you have a priori estimates method, and you have this 3-step method for dimension 4 or dimension 3. Every dimension 2, you have this destroyer Fourier transform method. Now, combining all these methods, now you can almost deal with all kind of singularity formations for geometric physical flows. The first one is harmonic flow, and in this paper with Juan Davila Manuel, we are able to construct both forward and even backward blocks, and we can also construct spontaneous blocks without assuming any video assumption on the initial conditions. And you can also do fractions, okay, non-local. And this is a harmonic map with about free boundary, which is a non-local half harmonic maps. And you can also, in this case, you also have a finite time block. But if you do the half harmonic map, ut plus square root minus u, and you don't have finite time block, you have infinite time block. But our theory also works for infinite time block. Right? And you can also do Yang-Mills. And so recently we also work on the Yang-Mills. For the Yang-Mills is you have a gauge, it's more complicated, and the Walton proof that in dimension 4 you have global existence. But what we say Yannick and then we show that actually for this flow you have blowup at infinity. Okay, you don't have finite time blowup, but for the Yang-Mills you have blowup at infinity. So you have an infinite time blowup for the young males. And for so all these are geometric flows. So another flow is the physical flow, is the nematic nickel crystal flow. So this is a flow that combines the Navier-Stokes and harmonic map. So this in this flow you don't see any structure. Okay, you don't see any structure. Now with Lai and Fang Huanin and Changyue Wang and Yif Zhou, and we are also able to construct finite time blowup for this combination of harmonic map flow and the Navier-Stokes. And we can show actually the Navier-Stokes in 2D, if you combine with harmonic map, also has a singularity. Has a singularity. So this method actually is very powerful. It works for any non-radio and radio case. And finally, for the edge system, we can also have construct the finite time blowup for the edge system. And this is a very complicated. This is the R2 case. In this paper, we developed the distorted Fourier transform for the R2. Okay, so and also the Kinder signal, which is another critical exponent problem and very complicated. And we can use this theory also to construct the infinite time and the finite time problems. And so summary, we have the parabolic going for n greater than 5 for L2 case, L2 2, 3, 4, and this method is not only useful to construct solutions, but it also can be used to analyze the singularities. And we call it reverse parabolic Green method. And for this, I have to refer to this paper. Here in this paper, we developed the reverse parabolic Green. And we've shown that if you have a temperature blowup, then what it should be exactly the one we constructed. And then from this, we get the non-existence of type 2 blowup. Okay, so this is the end of my lecture, and I thank you.